at some problems in Chapter 18, electrochemical problems, where we have a galvanic cell or voltaic cell where there is a voltage that's generated from having different concentrations of the same ion. So before we get to solving a problem, let's just kind of think about this a little bit. Which one is going to have more entropy, do you suppose? We've got situation A and situation B. Situation A, we've got just water, and here we have 1 molar sodium chloride. Situation B, it's 0.5 molar sodium chloride and 0.5 molar sodium chloride in 2 separate containers. And so maybe take your guess. What do you think? What do you think? Okay, more entropy, we'd say this one, right? In this one, we've got the sodium chloride, which is concentrated, and I don't know, maybe it can be a muddled argument, but anyway, this one's going to be more entropy. If we're going to make this situation, what we would do is we mix these, they become uniform, and now we have this. So nature is going to kind of prefer, right? Is going to prefer this situation to this situation. Nature tends to have things kind of mixed up, and nature tends to have things, if there's more states that they can be in, that's what nature seems to prefer. So going from A to B, going from this situation to this situation, what is delta S? So we would say delta S is positive. And if we go from B to A, right, maybe if we're doing some sort of reverse osmosis, right, we gotta work to do this, and we push all the ions back into one of these, we would say that delta S would be negative. So what's the effect on delta G for each of these situations, right? If we have a positive delta S, that makes delta G more negative. So this lowers it. And the other one raises it. So lowering it is something that would make a process more thermodynamically favorable, more spontaneous. So this is a process that's going to tend to happen. And the interesting thing about this is that, yeah, mixing kind of makes sense, but we can actually do this using an anode and a cathode, and electrons will flow to make this situation happen. That's kind of neat. This is from your textbook. It's page 888, number 158, and mention a few things first. So positive delta S means the energy is coming out of the system, right? Some part of free energy is entropy. So if we have a positive delta S, that's going to make delta G more negative, which means energy is coming out of the system. So this energy that's coming out can be made into, it can be electrical, right? So that energy can take different forms, but we can get electricity out of this. We can get a voltage. So Nernst equation, just a reminder, your textbook uses log, so they have a different constant here, and sometimes the numbers get to be a little bit different. I'm going to go ahead and use this just to show you that it doesn't matter a whole lot which one you use. So we have the Nernst equation, you got to keep this in mind. Here is the problem. We have a voltage of 0.58 volts. Here is your porous, this is what is your salt bridge. It allows ions to flow so that the charge will be maintained. This is like a porous disc or something like that. So charge can be maintained. Anyway, it's different than having some sort of paper salt bridge or something else. So we have 1 molar chloride here, and we have, question is, what is the concentration of Ag plus if the voltage is 0.58 and it's 1 molar silver over there? It's probably silver nitrate, but we don't really worry about the nitrate in this situation. So for the question, they ask you to label the anode, the cathode, the direction of the electron flow, and then to determine KSP. Oh, by the way, if you want to see a derivation of Nernst, see my video, made that last year, I guess. So let's figure out like which of these is going to be the anode and which is going to be the cathode. Well, I guess we can stay right here. We've got Ag+, this is going to be a very low concentration. We don't know exactly what it is yet, but it's going to be low. This is 1 molar. So what's going to tend to happen? Right, we've got last board. Right. This is the situation that's more favorable. Right? Not where one's really, really concentrated, the other has nothing. This is more favorable. So if we look at these two cells, you should be thinking, oh, well, that concentration should go down, and that concentration should go up. So if this concentration is going to go down, that means that the silver plus is going to be gaining electrons. If it's gaining electrons, we call that reduction, and that would be your cathode. Right, so this, the electrode should be a piece of silver. This silver is where you're going to have your anode. Electrons are going to be coming off of that silver, and the electrons are going to flow up here, right? So the electrons go that way. All right, so that's part A. Label that. Wrote a few things. All right, so I wrote out something ahead of time. The lower concentration of silver should have a higher cut. It should tend to get higher. So if ever you look at these two cells and it's the same ion in both half cells, whichever one is lower, that concentration is going to tend to go up. So whichever cell has the lower concentration of the ion, that's going to increase. So that's going to be where your anode is, or that'll be your anode half cell. So here is the oxidation reaction. That has a voltage of a potential of negative 0.80 volts. Here's the reduction, has a potential of 0.8 volts. You add them together and you get 0. So this is where you look at it first, you're like, well, what's going on? This is our E naught. Under standard conditions, 1 molar and 1 atm for gases, but here's just 1 molar for ions. It would be 0. So that tells us if the concentrations were the same, there would be no potential between the two cells. It would just stay like that. So we go back to Nernst, right? E equals E naught, and we have this, lnq. So lnq, anytime you have two cells that have the same concentration, whether it's 1 molar or 0.5 molar, once they're the same, Q is then 1, and then the ln of 1 is 0. So, but we do have a different concentration. Therefore, we are going to get a potential. So for this one, you're just going to plug in the values that they gave you, and it was 0.58 for the E. E naught is 0. N is 1. There's 1 electron that's transferred. And then ln of Q. So if you solve this, you get negative 22.568 equals lnq, and then I'll go up here. So Q is going to end up equaling 1.58 times 10 to the negative 10th. So Q, I can get rid of this. Is products over reactants. So the reactant, the one we go back to our diagram, the reactant silver ion is this one. The product silver ion is this one. So the reactant silver ion is 1 molar. They make nice numbers for you. So this is 1. This is your Ag plus in your anode. Q is 1.58 times 10 to the negative 10. So now we have the silver concentration. We do need to think about something still. So that's not what they ask you for. They ask you for the KSP. KSP for silver chloride will be silver times the concentration of chloride. And they made this nice and easy for you. They told you that the concentration of chloride was 1 molar. Therefore, 1 times 1.58 times 10 to the negative 10th is going to give you a KSP of 1.58 times 10 to the negative 10. All right, so we'll see. That's it. That's number 158, and we'll see. I can show you how it's done. So we're looking at a triple 20. Let's see if we. It's been a while. Got to make regulation. Oh, okay. I mean, that was close. I could do more, but this might be about as good as it gets. I mean, triple 20. You know, that's all for today.